In this video, I'm going to walk through a custom composer callback that I wrote with Claude's help and talk about what I found and the process involved. And this is also a blog post version that I'll put in the video description as well. So for some background, I'm working on a research project where we're training models with LLM-Foundry, and most of us in the group are new to LLM-Foundry, so there's a pretty steep learning curve, but we are learning a lot. And something that we wanted to understand as we are preparing our data sets, pre-processing our data sets, tokenizing our data sets, we want to make sure we're doing it correctly. And in order to understand whether, what does correctly mean, we want to look at a data set that's processed by LLM-Foundry and look at a batch and see how it passes through the model and passes through the loss function given the model's predictions. So in order to do this, I wrote a LossInspector callback, which I'm going to deep dive in this video. This is the third callback I've written for Composer. The first two, I have links in this blog post. I also have a video where I talk about writing a custom Composer callback. And I followed the same general process each time. The first couple dozen iterations is, I initially start out with vibe coding. So Claude, I give Claude a lot of context and I give it some requirements and I have a general sense of what I'm trying to do. Although not always, I start out with one idea and, you end up somewhere else at the end. And Claude will spit out this very verbose, lots of checks and comments and print statements, and I might clean it up a little bit, but I'll just copy paste it, throw it into the LLM-Foundry code. The file in LLM-Foundry that you're going to want to insert this callback into is most likely going to be in the command utils folder in train.py around line 650, 670, basically before the trainer is instantiated. And yeah, so I'll do that, the first time, and then if it works, then I'll start trimming it down and, changing different things and trying different things out. And eventually I'll try to get to a very bare bones minimum callback where if I can read through it and explain it, then I've done a good job of working with Claude to come to a solution. This particular callback took 27 commits from the very first one to the very last one. It actually started out as 3 different callbacks. I had one to inspect the embedding input outputs, one to inspect input outputs to the forward pass of the model, and one to inspect the loss function. And then over those 27 commits, we've got it down to one callback. So there's 3 events that I'm focused on in Composer's training loop. And as a quick reference, I'm going to show this documentation of here are all the different events that happen during the training loop that you have access to inside your callbacks. And so this is, Jeremy Howard's two-way callback system that FastAI implements and Composer has built on with that same philosophy. And it's probably one of the coolest things I've interacted with. It completely unlocks your potential to inspect what's actually going on in the model, and it's really empowering, and I am really enjoying learning about it. So there's 3 events that I care about. Before loss, so I want to capture the batch before it goes through the loss function. Before forward, I want to capture the input IDs and labels, and then after loss, I want to calculate the loss, quote unquote manually. And then I want to calculate the loss capture the loss that's been automatically calculated by the trainer via the model. And so this is what my callback looks like. So you need to import these objects / libraries. And I'm calling this LossInspector. One thing that would have been nice, every iteration Claude kept changing the name of the callback, so that was a little annoying. So that's what I would do differently. One thing I would do differently is keep the name the same. But anyways, we have this loss inspector, and it inherits from the callback class that comes from Composer. We're going to set some initial values that we'll take a look at in a second. And then we have our before loss, we have before forward, and after loss. After loss is the longest one, but it's mainly just, print statements that really take up space. So before loss, I have this self-inspected, arguably don't need it, but it just kind of ensures that I'm only doing one batch. I just ran training for one batch, so that was kind of how I controlled the logging. I'm going to grab the outputs from state, and the state is something that is passed to every event in Composer, as is the logger. And then I'm going to capture the state batch and store that in these attributes. So that's before loss. Before forward, I'm going to do a similar thing, but I'm going to grab the input IDs and the labels and store those. And then after loss, here's where we actually do all of our work. So state has a loss attribute, so we're going to grab that and we're going to print that out. So we're calling that the framework's loss. I'm going to get the logits from the state output, and I'm going to get the labels from the state batch. And again, from the state's model, we're going to grab the vocab size. And then calling the loss function of the model, I'm going to calculate what we're calling the direct loss. Why am I doing this? Well, I wanted to, number one, make sure I understand, what's the minimum number of arguments that you have to pass to the loss function. And even zooming out more than that, I had to considerably dig to figure out what the loss function even was, that it was even accessed from state.model.model.loss function. So those were kind of the two main reasons. Then we print that out. And then I wanted to understand, what are we actually dealing with here, right? So by now, you've heard of look at your data, right? That's the single most important thing you can do as a researcher, as a practitioner. And so we're literally going to look at the data. And because this is a tensor, and that when we print a tensor, it truncates, we're going to convert this to list. And we're going to look at that tensor as a list. Yeah, so that was the issue here with input IDs. Then we are decoding our input IDs. So again, we access the tokenizer from state, from model, and then we print out the actual decoded text. And then we do the same thing for labels. The labels are a bit more involved because in order to decode the labels, we have to remove all of the tokens that are the loss ignore index of -100. So we filter those out, and then we pass only those valid labels, and then we print the decoded value. And then one thing I wanted to make sure, this was purely just a sanity check, is like, are these input IDs and labels, are they the same as before forward? Like after forward, after loss, like does anything happen to these input IDs and labels, or are they the same as before? Which was why I saved input IDs and labels in self, and then we set self-inspected to true. And yeah, then you append this to the list of callbacks that's already accumulated in the LLM-Foundry script, and that's passed to the Composer trainer, and then you're good to go. So that is the overview of the callback itself. We're going to look at the outputs and all these print statements. We'll look at that in a second. But first, we're going to take a bit of a detour, and we're going to look at the small LM 135 million parameter model's loss function. And as I mentioned, I was surprised at how hard it was for me to figure out what is the exact definition of this loss function. Now, obviously, I'm just exposing my lack of familiarity with Composer and Hugging Face models, so that's a factor here. It's a skill issue there as well. So I was looking at the Composer documentation and source code, and some other comments had some of these examples, and it was helpful, right? Like, okay, cool, this is what I expect it to look like. The loss takes outputs, it takes targets, and it's using cross entropy, and okay, cool, it's not using the inputs, it's just focusing the targets. Like, all that was great. Good sanity checks. Looked at their mix-up algorithm, and this was kind of the first clue where I'm like, okay, cool. Like the batch itself, when they're modifying it, they're just passing it a tuple. So for a minute I was kind of experimenting, like passing different values as the input and the target, see if that changed the loss, but it didn't. And then it led me to this where I'm like, okay, state.model.loss. So if you look at state.model.loss, and while we're here, let me remove this extra indent. If you look at state.model.loss, at first glance, I was like, this is not helpful. It's not using the batch, like it's not doing anything. But then I realized that, okay, the fact that it's grabbing loss from outputs means that the loss is contained in the outputs, right? That's obviously what we're seeing. But what that meant was that the outputs come from the forward pass. That means the loss is calculated in the forward pass. So that led me to download the model. And this is something that I haven't used before because I always use notebooks, but even in notebooks, this was helpful. I import inspect, and I took a look at the forward pass. So we're going to do the same thing here. And, much of the forward pass is as you would expect: input IDs, attention mask, etc., etc. And then I think it was what caught my attention was this right here. So there we go. So this jumped out off the screen, and I'm like, finally, here is our loss function. So the loss function is self, which is the model dot loss function. So I'm like, okay, cool. It takes the logits, it takes the labels, it takes the vocab size, and then it takes other keyword arguments. But the key thing is it does not take the input IDs, which was something I was not sure about. So let's see. Yeah. So then we go to model.loss function. And if we run that, we get this. And this is where I finally could see, what is the loss function that my model uses. And the most important part for understanding is these 4 lines of code here. And shift labels is none, which it defaults to, because as we saw in the forward pass, it doesn't pass anything for shift labels. And so if shift labels is none, what does it do? It calls nn.functional.pad, it passes label, it passes this tuple, and then it passes this value. And then the shift labels here, it takes all of the previous dimensions stay the same, but then the last dimension, it takes the value starting from index 1. So it skips the first value. And so this is where, I was looking at this for a minute and talking to Claude and thinking about this, and I finally realized, I'm like, oh, okay, like this is actually telling me a lot about how the labels are, kind of what the labels values are before we get to the loss function. And basically the labels are not shifted. The loss function itself is doing the shifting. So we're going to take a look at that in a second. But I wanted to walk through this nn.functional.pad. And we'll come to that in a second as well. So here I've just made up some labels as a tensor. And then I imported pad from torch nn functional. And so labels is the thing that you want to pad. The tuple that you give it is, in this case, the last dimension. It's going to operate on the last dimension. And to the leftmost end, it's going to add no padding tokens. And to the rightmost end, it's going to add a padding token. And the value of the padding token is whatever you give it here, which is -100, which is the value that the loss function ignores. So 3642 gets padded as 3642 -100. If I did 1, 0 as this value, then it would pad it to the left. If I did 1, 1, it would pad it to both left and right. So I'm going to pad it just to the right, and then I'm going to pull all values except for the first one. So I have effectively now shifted my labels to the left by 1 element. And why is this important? Well, our logits are predicting the next token. So here's, if the context, the batch item that we're training on is the cat sat on the table, the first token is and the first predicted token, and the first position in the logits is going to correspond to this cat token. And then the cat is going to inform what comes next, which is sat, and then the cat sat informs on, the cat sat on informs the the cat sat on the informs table. So our logits, cat sat on the table, those positions are already shifted by 1. Like the logits don't need any shifting. But our labels, which is just, in this case, it is just a copy of our input IDs, positionally the same, and we'll look at the differences there. But the input IDs has both, in this case, I'm using a QA data set, so the input ID has both the prompt and the response and padding tokens. The labels has the prompt tokens replaced with -100, the padding tokens replaced with -100, and it has the response tokens as the actual tokens. But it's not shifted yet, right? It's still an exact copy positionally of the input IDs. So to align it with our logits that are, offset by 1, we have to perform this shifting operation. And to make sure that the last token doesn't predict anything else, we're going to make the last value a -100, so it's ignored in the loss calculations. Okay, so at this point, I'm going to open up a screenshot that shows, visually the difference between the input IDs and the labels. Okay, so this is what I printed out, and this is why I converted the input IDs and the labels to list so that it would print out the entire 2048 token sequence. And then in Notepad, I just searched for from token 1882 to token 0. That span of tokens is the response in the QA dataset. And so I searched for that token and highlighted it here. And then you can see that there's also the same sequence of tokens up here in the prompt, in the input IDs, because we have our prompt starting from token 49 ending at 47, and then we have our response 1882 to 0, and then small LM2 135 million uses the end of stream token as the padding token, so the rest is padded with zeros. But this was, really critical for me to see. It was very pivotal for me to see because now I completely understood. I'm like, okay, got it. Input IDs, labels have the exact same positioning. The only difference is that the input IDs has the prompt tokens, whereas the labels has -100s. Both have the response tokens. And then after the EOS token here of 0, we go back to having -100s, whereas in input IDs, we have the EOS token repeated as padding. So this was, a really nice way to just, with certainty understand how is a prompt response dataset item in terms of input IDs and labels, how is it handled by the data loader? And this also shows us why we need to shift things to the left, because right now the input IDs and the labels have the same positioning. And we want to offset by 1 because we're trying to predict for each token here, we're trying to predict the next token. Okay, so that's a brief detour into the loss function, also looking at input IDs and labels. Let's now go back to our callback logs, and we already saw these two here, but the 4 key print statements was the framework loss output, which is 1067513, the direct model .loss function call, and this was a confirmation that, okay, I know how the loss function works, I know what arguments to pass to it, and it gives me the correct loss value. So that was a really rewarding experience to see these two match. It was definitely one of those exciting moments when you're staring at the terminal looking for outputs, and then we have those there. Yeah, so the last thing I'll do just to show what this looks like, this comes from the MetaMath QA dataset. That's the dataset that we're looking at. And here is the prompt, and here is the response, and here is the end of sequence in the response. So when we were looking at, tokens 49 to 47, we were looking at, a box, what is the value of unknown variable x? And then when we were looking at 1882 0, we are given that a box, the answer is 50, end of text. And so now I know that when I process a new data set, I know what to expect I should see something like this when I print out the input IDs and the labels. I should be able to check that the loss function calculates what I expect, and I should be able to, make sure that, well, I don't really have to make sure of this, but at least now I understand that the data loader is not shifting the labels by one. That's being handled by the loss function. In this type of research, when we get to the point that we want to implement our own models, this is, really critical to understand that if we are, implementing our own loss function, we have to make sure that we, shift it by one. Otherwise, the model is, I guess it's not even cheating. It's just predicting the wrong. So I think that's it for this video. Really interesting experience for me, really rewarding experience. I think, I value the experience of vibe coding, but then I also value the couple dozen iterations of whittling down the code to something that makes sense. That's something that I can explain. And yeah, now we have a callback that we can use, and this is now the third callback that we can use to inspect what's going on inside the model, so that when we try out different techniques, different data sets, we can, run these sanity checks to make sure things are working as expected. So that's it for this video. Thank you for watching, and I'll see you next time.